Hello everyone, welcome to this video looking at trigonometric substitution. So there is good news and bad news. The good news is that we are going to be able to use all the techniques that we just studied in calculating integrals with trig functions to evaluate even more integrals. We're going to see that we can even use trig functions to calculate integrals that don't seem to have trig functions in it all to start with. So that's the good news. And then the bad news is, well, it has trig functions and people seem to find trig functions and trig identity is really difficult. But okay, let's get through it together. So here's a motivating example just to see kind of what's happening. So let's suppose we want to integrate something like the square root of a squared minus x squared, where a is a constant. So it could be the square root of 1 minus x squared, it could be the square root of 9 minus x squared, it could be the square root of 50 minus x squared, whatever. And you might be tempted to jump in and use u equals a squared minus x squared. But there is a problem here. Remember that we said substitutions are particularly good if we have a composite function times the derivative of the inside. So if we were using u equals a squared minus x squared, we might hope to have an x term out in front in order to actually make the substitution go through smoothly. And we don't here. So actually that substitution doesn't work out too well because when we try to rearrange that dx into du's, it will create more square roots. So u equals a squared minus x squared is not a great substitution. That would work better for if we have things like x squared root of a squared minus x squared. Okay, so what can we do? And just imagine for a second that a squared was, a was 1. Suppose we had the square root of 1 minus x squared. Then, okay, we remember that 1 minus sine squared is cosine squared. So then it would be really nice if that x squared was a sine squared, for instance. And actually, that's what is the correct thing to do, right? We should substitute a trig function and then use the things with the identities with squares of trig functions to change to a different square, and then we can actually simplify that square root. So we're going to use trig identities here. So let's see how it plays out. Let's start with x equals a sine theta. And this is a little different to the normal substitutions that we've seen before. Everything is going to work mostly the same way. But normally when we do a substitution, we would choose u equals something. Our new variable is written in terms of the old variable, right? We have u equals x squared or u equals e to the x or u equals sine theta or whatever. Before, our new variable was written in terms of the old variable, and now it's the other way around, right? Our old variable x is written in terms of the new variable theta. So it's just kind of swapped around. But the main steps in the substitution are the same. We have to replace everywhere the old variable appears, we have to write it in terms of the new variable. And everywhere the dx or the d of the old variable appears, we have to write that in terms of d of the new variable. So we need to rewrite this in terms of theta and d theta. So if we do that, we have, okay, dx over d theta is a times cosine theta. A was just a multiplicative constant. Differentiating sine with respect to theta gives cosine theta. Okay, so we have dx equals a cosine theta d theta. And actually things are now working out very smoothly because we can write dx we have immediately in terms of theta. And we can just replace everywhere we had an x by a theta. So let's go ahead and do that. So our integral, just focus on the top line. We're starting with the integral of the square root of a squared minus x squared. A squared is constant, it stays around. Okay, x squared becomes a squared sine squared, right? If x is equal to a sine theta, x squared is going to become a sine squared theta, a squared sine squared theta. And then the dx is going to become a cosine theta d theta, as we just said. And now we want to try to simplify this square root, which is the whole point of introducing this trigonometric function. So we see in both terms inside the square root, we have an a squared. So let's bring out the a squared. So then inside the square root, we're going to have a squared times 1 minus sine squared. And then we know always that sine squared plus cosine squared equals 1. So 1 minus sine squared then is going to become cosine squared. So we can replace this 1 minus sine squared by cosine squared. And now things look much better because inside we have the square root of a squared cosine squared. And we can just take the square roots of each piece separately. We get a times cosine of theta. Okay, but then once we have a cosine theta, there is another a cosine theta over here. So we get a cosine theta times a cosine theta. We have then a squared cosine squared theta. Okay, and now this is something that fits very well into the scheme of what we did before in 7.2. So this is an integral involving sine and cosine, and we have an even power of cosine. So we have a perfect method for how to do that, right? We write that as a half 1 plus cosine of 2 theta, and then we would integrate and so on. So then we would get an answer in terms of theta, and then as usual with substitution, we would have to go back and write it in terms of x. Okay, but the key point here is I'm not going to go through the substitution in this example. I'm not going to go through the remaining steps here, but the main point was we started with an integral involving, square root of some particular expression. We're going to see there are 3 types of expressions where this works in a moment. And we introduced a trig function, and then introducing the trig function and using trig identities enabled us to simplify that square root. And then we got a much easier integral that we could actually handle with trig functions. Okay, so and just to emphasize, you might be tempted to jump in and do u equals a squared minus x squared, but that's not going to work. That would be much better if we had things like x square root of a squared minus x squared, because that x term would enable us to change the x dx into du or d theta. Okay, so let's see what are some other examples where this works. So as usual, if you're thinking about using substitution, check to see if a naive substitution works. Just u equals whatever the inside looks like. So remember, these work particularly well if you have a composite function and then somewhere you have a multiple of the derivative of the inside. So for instance, if you had, either the sine theta times cosine of theta, or you had sine of x squared times x, things like this, where you have the derivative of the inside, then just jumping in with a naive substitution works. But when do we have to use this kind of sneaky trick with trigonometric functions? So if we cannot use a naive substitution, if we have things like the square root of a squared minus x squared, or it could be some other power involving square roots. So it could be to the power 3 over 2, or it could be 1 over the square root of a squared minus x squared, or 1 over 1 over x squared times a squared minus x squared, things like that. It doesn't necessarily have to just be the square root of a squared minus x squared, but probably a power that involves fractions, a fractional power with square roots. Okay, then we're going to substitute, as we just said, x equals a sine theta. And here, keep in mind, so it seems a little pedantic, but it's useful to keep in mind what are the values of theta that we're supposed to be using. So if we're looking at the square root of a squared minus x squared, the allowable values of x, a squared minus x squared has to be positive. So x has to be between minus a and plus a. So we need to be able to represent any x between minus a and plus a in the form x equals a sine theta. Okay, but that's okay provided sine theta is between minus 1 and 1. So we can use theta between minus pi over 2 and theta between minus pi over 2 and pi over 2. This is useful to keep in mind as well. If you're doing the square root of cosine squared, then you want to know that cosine is positive in order for the square root of cosine squared to be equal to plus cosine. Okay, but this is a little bit of a pedantic point. So the key takeaway is if we have the square root of a squared minus x squared, we're going to use x equals a sine theta. Okay, and then moving on, another type where we might use trig functions is if we have the square root of a squared plus x squared. And then, okay, what identity would be useful? If we remember sine squared plus cosine squared equals 1, divide both sides by cosine squared, we get 1 plus tan squared equals secant squared. So for things like this, we should use x equals a tangent theta. And then once we simplify the square root, it's going to give us things in terms of secant of theta. Okay, and then finally, if we have something like the square root of x squared minus a squared, then we're going to want to use x equals a secant theta with these values of theta. Okay, so these are things to keep in mind. Remember what is the correct type of substitution for each of these different integrals involving square roots. And as we said, it doesn't have to be just integrating this square root, it could be things involving this square root. Okay, and here are the identities we're going to have to use. Sine squared plus cosine squared equals 1, or 1 plus tan squared equals secant squared. Or if we rearrange this, right, secant squared minus 1 equals tangent squared is going to be used in the third one, but it's the same identity, just rearranged. And then at the end, so that the point of this was that it gives us an easier integral in terms of trig functions that we can actually do. But then at the end, it's going to give us an answer in terms of theta, whereas we started in terms of x. So we're going to have to put that answer in terms of theta back in terms of x at the end. And there are several different things we might have to do. So we might have to use trig identities. For instance, if we know what sine theta is in terms of x and we want to find cosine theta, then we'd want to replace cosine theta by the square root of 1 minus sine squared. Or if we did the thing with 7.2 where we convert to double angles from the last section, and we end up with an answer in terms of double angles, then we'll want to convert back. So we can convert from double angles back to single angles using these double angle formulae. Sine 2 theta is 2 sine theta cosine theta, or cosine 2 theta is 2 cosine squared theta minus 1, maybe something to add to your formula sheet. Or there is also the strategy with the SOHCAHTOA triangle that if we know some of the trig functions, we can calculate the others because we know sine is opposite of a hypotenuse, cosine is adjacent of a hypotenuse, tangent is opposite of or adjacent, and so on. Okay, so this is the overview of everything we're going to do in this section. Everything is just a variant of these three tricks. So let's see how it works. Let's go through a full example. So let's suppose we look at the integral of the square root of 9 minus x squared divided by x squared dx. Okay, if we just had x squared 9 minus x squared, then we would do u equals 9 minus x squared. But we don't have that, we have something more complicated. So we're going to want to consider a trig substitution. And we see that the square root involves 9 minus x squared. So we're going to want to try x equals 3 sine theta based on what we just said. Right, it's important to start with the 3 because then when we square the 3, we will get the 9 and everything will simplify. So let's try x equals 3 sine theta with our values of theta between minus pi over 2 and pi over 2. Then we want to be able to write everything in terms of theta. So we're going to substitute in x equals 3 sine theta. And we also have to substitute dx. Okay, so if x is 3 sine, dx d theta is 3 cosine. So dx is going to be 3 cosine d theta. And then if we simplify this pesky square root, just replacing x by 3 sine theta, x squared becomes 9 sine squared. 9 sine squared theta. We pull out the 9, we get 9 times 1 minus sine squared theta. And then 1 minus sine squared theta becomes cosine squared theta. So we end up with 9, the square root of 9 cosine squared theta, and then we square root each piece. Square root of 9 is 3, square root of cosine squared theta. Since we're in the right half of the unit square, we get 3 plus cosine theta, 3 times the positive cosine theta. Okay, and now we can just jump in and substitute everything. So the top, the square root we just talked about becomes 3 cosine theta, just using 1 minus sine squared equals cosine squared and doing the square root as we said. The bottom x squared becomes 9 sine squared theta. Dx becomes 3 cosine theta d theta, as we said. So we have some huge mess, and then we have to look at what we can simplify. So we have a 3 and a 3 on the top, and we have a 9 on the bottom. So those are going to get simplified straight away. And then we have a cosine and a cosine on the top. So that's cosine squared on the top. And we have sine squared on the bottom. So we have cosine squared divided by sine squared. Okay, cosine divided by sine is cotangent. So we have the integral of cotangent squared theta d theta. And then cotangent and cosecant, we briefly commented on the last section, but we didn't talk about too much. But remember, we said the idea with cotangent and cosecant is to remember they are kind of the evil twin of tangent and secant. So cotangent behaves a little bit like tangent. Cosecant behaves a little bit like secant. So if we're looking at finding the integral of cotangent squared, let's imagine we were looking at the integral of tangent squared. Then the strategy will be to convert to secant squared. So in this case, we're going to convert to cosecant squared if we do the analogous thing. So if we take our identity sine squared plus cosine squared equals 1, divide both sides by sine squared, we get cotangent squared is cosecant squared minus 1. So now we have to integrate cosecant squared. Remember we said the integral of secant squared is tangent. The integral of the evil twin cosecant squared is minus cotangent. So everything behaves kind of the same way with the evil twin ones, but we have to add on a negative sign. So we're getting minus cotangent theta, and then the minus 1 integrates to minus theta, and then we have plus c. So this was a way easier integral that we were actually able to do in terms of trig functions. Now the last step is just to write this back in terms of x, because we started with an indefinite integral in terms of x. So here is our task to conclude. And to do that, we have to use our substitution. So x was equal to 3 sine theta. So let's try to write each piece of the integral back in terms of x. So we have to write cotangent theta in terms of x. There are different ways to do this. You could use the triangle if you like. But for instance, I wrote cotangent of theta is cosine divided by sine. We know something about sine, right? X is 3 sine theta, so sine theta will be x divided by 3. So we know how to calculate sine. So if we can somehow write cotangent all in terms of sine, then we can just substitute sine is x divided by 3. Okay, so cotangent is cosine divided by sine, and then we want to write the cosine in terms of sine. Well, that's going to be square root of 1 minus sine squared. So now we have everything in terms of sine. We could just replace sine by x divided by 3. So we are getting on the top square root of 1 minus x divided by 3 squared. On the bottom, we have x divided by 3. Okay, now we just have to simplify. If we multiply top and bottom by 3, the bottom becomes x. If we multiply the top by 3, and we take that inside the square root, that's going to become multiplying by 9. So the top is going to become the square root of 9 minus x squared. Okay, so in the end, there is a little bit of algebra, but cotangent of theta became square root of 9 minus x squared divided by x. Okay, and then the other piece was theta. Well, if x is 3 sine theta is x divided by 3. The best you can do is theta is inverse sine of x over 3. So when you have things that are a composition of a trig function and an inverse trig, we can hope to simplify those in a nice way. But if it's just an inverse sine of something, there is no way to simplify inverse sine. You just have to use the inverse sine function. Okay, so now we can write out the answer just putting it together. So we said our integral that we started with was minus cotangent theta minus theta plus c, and then we worked out minus cotangent theta, we worked out minus theta. So now we have an answer back in terms of x. And if you were really patient, you could multiply, you could differentiate this and check it was the correct answer that we started with. But probably we are sick of this example by now, so let's not do that. So the strategy was x equals 3 sine theta, dx equals 3 cosine theta d theta, write everything as a trig function. It's going to become an easier integral. We use the techniques from the last section to do that. Then at the end, we have to write the answer back in terms of x. So that was what we did. Okay, so let's look at some more kind of variants. So all the examples in the table we just talked about behave kind of similarly. So the ones with sine, the ones with tangent, the one with secant. So based on what you're seeing, just use the right identity. But here is one that seems like it doesn't fit in the table exactly, but we're going to see with a simple tweak, it does fit into that scheme. So we're looking at the definite integral from 0 to 3 square root 3 over 2 of x cubed divided by 4x squared plus 9 to the power 3 over 2 dx. And the thing on the bottom is, it's not a square root, but it is a square root and then cube. It's to the power 3 over 2. So it's kind of the kind of thing that we would use the techniques from the table for. The only place where it doesn't really fit is that instead of having x squared plus a squared, or a squared minus x squared, or x squared minus a squared, in all the examples we saw in the table, all the cases, there was nothing in front of the x squared. It was just a 1. Whereas here we have a 4. So let's see how to adjust what we do to take into account that 4. So if we go by analogy, if we didn't have that 4 there, we would have the power 3 over 2 of x squared plus 9. So we would be looking at the table with all the different cases with the square root of x squared plus 9. And based on the cases we talked about, we would use x equals 3 tangent of theta. And then we would get 9 tangent squared theta plus 9, and we would use tan squared plus 1 equals secant squared. We'll be able to simplify the square root nicely. The problem is, if we jump in and use 3 tangent theta here, the coefficients are not going to line up for us to simplify. So we're going to have to do something slightly different with 4x squared plus 9 to the power 3 over 2. And the trick is that we want to get rid of this 4 because this 4 is making our life miserable. So we want to somehow simplify so that we can cancel this 4. So we have to think, what do we have to divide x by if we're going to cancel the 4? And if we just divide the x by 4, then after we square it, we're going to be dividing by 16, which is not going to be any good. So we actually have to divide by the square root of 4, which is 2. So instead of using 3 tangent theta, we're going to use 3 over 2 tangent theta, because then once we do x squared, we're going to be dividing by 4, and that's going to cancel with the 4 here. So we're going to be back into the land where everything works. Okay, so let's see how that works. So let's go ahead and use x equals 3 over 2 tangent theta, dividing by the square root of that coefficient in front of the x squared. Then dx over d theta is going to be 3 over 2 secant squared theta d theta. So we can write dx in terms of d theta. And then the next task was to simplify this power 3 over 2. So as we talked about, x squared is going to become 9 over 4 tangent squared, and then we have to multiply by the 4. So we have 9 over 4 tangent squared times 4. The 4s are going to cancel. We're left with 9 tangent squared theta. And then we have the extra plus 9 over here. Okay, now we can simplify this because we know tangent squared theta plus 1 equals secant squared theta. So 9 tangent squared theta plus 9 is going to be equal to 9 secant squared theta. So now instead of having 2 terms inside the square root, we have just 1 term. Then we can take the root of each term separately. So if we want to raise something to the power 3 over 2, we can do 9 to the 3 over 2 times secant squared to the power 3 over 2. Let's do this. We just have to do the square root first and then cube it. So if we do the square root of 9, we get 3. We cube it, we get 27. If we do the square root of secant squared, we get secant. Then we cube it, we have secant cubed. So now we managed to write this complicated term just in terms of theta. Okay, so let's go ahead and substitute everything in. So the x is going to become 3 over 2 cubed tangent cubed theta. The square root on the bottom we just worked out. We said it was 27 secant cubed theta. And then the dx we also worked out. We said it was 3 over 2 secant squared theta d theta. And then the limits changed, of course. So again, as usual with substitution, we should change the limits if we have a definite integral. So how do the limits come about? Well, we look at x equals 3 tangent theta. And okay, the x limit before was x equals 0 on the bottom. So we have to work out what is the value of theta when x equals 0. So 0 equals 3 tangent of theta. Tangent of theta equals 0. Okay, we're going to have theta equals 0. And then for the top limit, we have to look at what happens when x equals 3 square root 3 over 2. So if x is 3 square root 3 over 2, if we simplify, we're going to get tangent theta equals square root 3. So theta is pi over 3. The upper one is kind of a pain. You have to write it out and simplify some 3s and think about your trig functions. So that's not the main point here. You can just take it for granted that the top limit becomes pi over 3. Don't let it mess you up. The only tricky thing, the only new thing here is what substitution we did. We divided by the 2 because after squaring, we want to cancel the 4. And then we write everything in terms of theta. So everything is as normal once we pick the right substitution. And then we have to try to simplify because it looks like we have a huge mess. So if we just look at the constants first, we have 3 cubed, which is 27. And then we have a 27 on the bottom, so those are going to cancel. And then we have another 3 on the top. So we're going to be left with 3 on the top. And then if we look at the 2's, we have dividing by 2 cubed, so dividing by 8, and we have divided by 2. So that's going to become dividing by 16. So for the constants, we're going to have 3 divided by 16. And then if we look at the terms involving theta, we have tangent cubed of theta times secant squared divided by secant cubed. So secant squared divided by secant cubed is going to become dividing by secant. So after all that simplifying, we have to deal with the integral of tangent cubed divided by secant theta. And now it's a mess involving tangent and secant that doesn't seem to fit into anything that we talked about in the last section. So right now we might be tempted to panic. If you ever have a mess involving tangent and secant or cotangent and cosecant and you're not sure what to do with it, One strategy is to write it back in terms of sine and cosine and see if it gets any better, because they are much easier to work with. So if we do that, we have the integral of sine cubed divided by cosine squared times 3 over 16. So now we just have to think about the integral of sine cubed divided by cosine squared. And sorry, so this is a much easier integral than the one we started with. So let's see how to do that instead. And since it's a definite integral, we're not going to have to go back to the old variable here. So that's an advantage. So here is our new problem. And it doesn't seem that it really fits into the scheme of last time, but we can use the same methods, because on the top we have an odd power of sine. So if we split off a sine, we're going to be left with sine squared. And then the sine squared we can replace by 1 minus cosine squared. So we can actually write this, just keeping a sine, converting the rest to 1 minus cosine squared. We have sine theta times some big mess involving cosine. This is perfect for our substitution, right? We have a composite function, and then we have the derivative of the inside. We can do it, jump in and do a substitution u equals cosine theta here. So let's apply the substitution u equals cosine theta. Then du over d theta is going to be minus sine theta. So if we go ahead and do our substitution, what do we have? So sine theta d theta becomes minus du. So we are going to get minus 3 divided by 16. Then we have the limits. So we have to find the new limits. Okay, when theta is 0, u becomes 1. And when theta is pi over 3, u becomes cosine of pi over 3, which is a half. And then on the inside, we already used the sine theta d theta to become minus du. Everywhere we have a cosine, that's going to be replaced by u. So we have 1 minus u squared divided by u squared du. Okay, so all we did was apply the substitution, u equals cosine theta. And now this is an integral that we could do with, the first couple of, as soon as we started doing integration in Calc 1, we could do it with these. We can deal with this integral. All we have to do is divide each term by u squared. So we get 1 over u squared minus 1. And then if we bring in that minus sign, we're going to get 1 minus 1 over u squared. Okay, we have to integrate 1 minus 1 over u squared. Using the power rule, it's going to be u, and then we had minus u to the minus 2. So if we integrate, that's going to be plus u to the minus 1. So we're going to get plus 1 over u. From 1 to a half, okay, we plug in a half, we plug in 1, and we subtract them. We get 3 over 32. Okay, so this one was kind of long, but the only new point here was really that we didn't have x squared plus 9, in which case we would have used x equals 3 tangent theta. But if there is a coefficient in front of the x squared, you're going to want to go ahead and do what you normally would, but divide by the square root of that coefficient. Okay, so let's go on to the very last example. Here is maybe the most difficult one you could get. I don't know if you would see this in an exam, but just in case, I do want to talk about it. So let's suppose we had something like x divided by the square root of 3 minus 2x minus x squared. Then it doesn't look like a squared minus x squared, or x squared plus a squared, or x squared minus a squared. It doesn't look like any of the three in the table. And it's not just a multiple in front of the x squared either. There is this x term that doesn't appear in any of the other cases. So what should we do? And as I wrote in the title, the trick is to complete the square. So we're going to complete the square on this inner 3 minus 2x minus x squared term. And there are many different ways that people like to write completing the square. Personally, I like to forget about the constant because you can always add and subtract the constant later. And I don't like to have anything in front of my x squared. I just like to have x squared plus something. So that's why I moved the 3 over, and then I had a minus sign here, and then I stick everything involving x inside. So I just have 3 minus x squared plus 2x. And then I can complete the square on x squared plus 2x, which is just, x squared and then some multiple of x. And it's always x plus a half of whatever the coefficient is in front of the x squared. And then I have to subtract off the wrong term. So if I were to multiply this back out, I would get x squared plus 2x plus 1. But I didn't have a 1 inside my square bracket, so I want to subtract off that 1. Okay, and then I will multiply everything back out. I get 3 minus 1 is 4. And then minus x plus 1 squared. So probably I didn't help you, or I didn't teach you complete the square in those few moments, but use whatever trick that you like, or whatever method you like, or look it up if you're a little shaky on completing the square. But okay, the thing inside the square root becomes 4 minus x plus 1 squared. So if we rewrite it in that form, we have to integrate x divided by the square root of 4 minus x plus 1 squared. And the trick next is to replace u by x plus 1, is to replace x plus 1 by u. So if we use u equals x plus 1 and du equals dx, let's write everything then in terms of u. Okay, the bottom is kind of a pain. The x becomes u minus 1, right? U equals x plus 1, so x becomes u minus 1. But the bottom now becomes the square root of 4 minus u squared, and then we have the du, because u is x plus 1. So this becomes the integral of u minus 1 times the square root of 4 minus u squared du, and now the square root fits perfectly into the scheme of what we were talking about. Right, now it looks like a squared minus Okay, a squared minus u squared. So now we would do a trig substitution. So we would have to do u equals 2 sine of theta, just going back to the different cases we talked about. And okay, there are many steps. It gets kind of tedious. We've seen maybe two like that now. So we'd go through all the steps, replace the u by theta, du by d theta, find a simpler integral involving theta, simplify the square root, do the trig integral, then write the answer back in terms of u. Okay, and we would get minus the square root of 4 minus u squared minus arc sine of u divided by 2 plus c. And then because we already started with a substitution to get to this simpler integral involving u, we have to go back and write u equals x plus 1. So here there will be two substitutions and two replacements, right? One at each step. So we would replace u by x plus 1 and get this final answer. Just the previous one replacing u by x plus 1. Okay, so what was the new thing? The new thing here, the moral, is that if we have something that looks like actually, there's also this crossterm involving x. So it's not just a squared plus or minus x squared, but we have also this crossterm. We should start by completing the square and then doing a substitution where u is whatever is inside the square. And then it's going to bring us back into the land of whatever we were doing before. All right, so here we could do u equals 2 sine theta and so on. If you don't like doing two substitutions at a time, you could have done directly, once we see we have the square root of 4 minus x plus 1 squared, we really want this to become 4 sine squared. So we could do x plus 1 equals 2 sine theta. You could do it in one step. X will be 2 sine theta minus 1. But maybe that's more confusing. So I think it's maybe simpler just to do two steps in a substitution. Okay, so that's everything for 7.3. We'll do more examples in class, but the key takeaways are, there are three cases depending on what square root we have for how to simplify it using trig identities. So we're going to use either sine or tangent or secant. Make sure you remember which case is which. If there is something in front of that x squared, then we're going to have to divide by the square root of that coefficient so that everything will work. And if we have also a crossterm involving x, then we're going to want to start by completing the square. Okay, thanks everyone. See you next time.